When I was making my video about the planimeter, I had an idea that didn't really fit into that video, so here it is. If you don't know anything about planimeters, check out my other video here. This will probably only be interesting if you've seen a little bit of calculus. It'll probably be more interesting if you tried to learn or teach calculus recently, since the planimeter gives you a new way of thinking about the integral. The planimeter measures the area of any region in the plane, and just for fun I decided to measure the area between the x-axis and the graph of some common functions. If you know some calculus, you'll know where I'm headed with this. If you choose some starting x value and measure the area under the curve up to some other x value, and you do this over and over again, these areas give you another function called the integral. In calculus we write it like this, where the little f is the function that we're measuring, the a is the starting x value, and the variable x is that x value that we measure up to each time. There's a thing called the fundamental theorem of calculus. It says this new function, the big F, that's made up of the areas, is the antiderivative of the function we started with. That means the derivative of the big F is the same as the little f. It means if the little f is, y equals x, then the big F should be some function whose derivative is x, like maybe 1/2 x squared. Now I can use my planimeter to measure these areas, so we should be able to actually demonstrate that the integral of x is 1/2 x squared by measuring various areas with the planimeter and plotting all the answers. So I'm going to start with the graph of f of x equals x and try to compute and plot the values for the big F, that is the areas. Let's start with big F of 2. As an integral, we write it like this. That's the area bounded by the curve, the diagonal line, and the x-axis between x equals 0 and x equals 2. That makes a triangular shape. So I go around clockwise starting at the origin. And I got 1.7 for that area. So I'm going to plot y equals 1.7 at x equals 2. I'm going to do this again, but I go up to other values of x. Each time I measure the area up to some x, I plot that area right above that x value. Like I said in my other video, this planimeter isn't super accurate, but since I'm doing this over and over, hopefully my errors will kind of even out. And once I finish with the positive x values, I'm going to do the negative ones. Now, if you know some calculus, you might get a little worried a bit about areas below the y-axis, if they'll give you negative answers or not. When you compute the integral, you should count areas below the axis as negative, and also you should count areas as negative when your starting point is to the right of your end point. So the integral on these regions is actually negated twice for two different reasons and ends up being positive. Lucky for us, the planimeter also measures these areas as positive, but for a different reason. The planimeter measures the sine of the areas according to the orientation of the enclosing loop. And since I'm still going clockwise around these regions, they still count as positive. This type of reasoning, actually based on orientations of the enclosing loops, can lead you to some totally different proofs of some classical facts about the integral, like these ones. Anyway, this example turned out pretty well. The integral clearly looks like a parabola, and you can check that the y values I plotted match pretty closely with 1/2 x squared. Let's try another classic example. Here's the graph of y equals sine of x, graphed in radians. This time I'm going to trace the graph starting at pi over 2 as my starting point each time. That's because I want the graph of my answer to have y equals 0 when x equals pi over 2. Actually, the choice of the starting point will have an effect on what the graph of the answer looks like. But if you think about it, choosing different starting points corresponds just to choosing different values of the integration constant, which is another fun fact. Sorry for my head, it's blocking the picture. It's kind of hard to trace with the planimeter unless you're right on top of it. Here you see I really do get some negative area readings. That's because I'm going around those regions counterclockwise, which reads as negative in the planimeter. So it ends up looking like cosine, but flipped vertically, which is what we expect if we know some calculus. By the way, this is a real compelling reason to use radians. If I use degrees or some other arbitrary system instead, the y values would all be way off the scale. Something I always try to remind my students of, that formula that everybody knows, it's only true when you use radians. Otherwise, you would have to multiply by 360 over 2 pi. All right, I got two more examples. Here's a graph of 1 over x. I'm going to use x equal 1 as my starting point. And you can see eventually the answer looks like the natural log. And here's my favorite example, e to the x. This one you can really tell if the planimeter is being accurate, since with perfect accuracy, the red dots should end up right on the original graph every time. They're pretty close, right? Right? Perfect.